So here, if you set this up correctly, remember you can use pressures instead of concentrations, exactly the same. Set it equal to Kp and then solve, you should get 0.00244. Now, if you did not get this number, make sure that you square rooted to get the variable, in here. Okay, so let me know if you need help with that, but you should be able to do those ones pretty easily. Now, when you don't have all of the other information, so these examples up here were pretty easy because you're just missing one variable. Now, a lot of the times though, we want to try to calculate K and we only have like one equilibrium concentration. And there are ways to do that. And that's called using an ICE table. You will be using a lot of ICE tables in this semester. So you really should pay attention and get used to them. ICE tables can solve a lot of problems. If you can do ICE tables and you can do stoichiometry or dimensional analysis, you should be able to solve like every problem there is in chemistry. So I'm going to show you how to do an ICE table. Essentially, if something is a reversible reaction, you should be able to do an ICE table to figure out concentrations. Okay, so let's say you need to find multiple equilibrium concentrations instead of just one, or you need to calculate Kc or Kp, and all I gave you was the initial concentrations and like one equilibrium concentration. There's a whole bunch of uses for ICE tables. So what does ICE stand for and how do I set it up? So I stands for initial. Okay, so like the starting amounts of any reactants or products. Reactant or product, starting amount. Okay, so like how much you started out with. So usually we start with reactants and we want to know how many products there are at the end, but if it's reversible, we should have some reactants left over also. So there should be reactants and products in there at the same time. So the concentrations are going to change, and the C stands for how much they're going to change by. Change in concentration. Okay, so these are stoichiometric. And anytime I mention stoichiometry or stoichiometric, that just means that we're going to have to bring in the ratios of all of the reactants and products. Okay, so those coefficients are going to be really important. So those are stoichiometric. They're going to use those coefficients in order to figure out the change. And then E, of course, stands for the equilibrium amount, which is just a combination of my starting amount, or my initial, and the change. Combo of I and C. All right. So one thing that's extremely important to remember for ICE tables is you have to be in molarity or pressure. You cannot just use moles. It has to be moles per liter. It has to be some type of concentration or the values you would plug into a K equation, right? So that's going to be important to make sure you're in molarity, because a lot of times I'll just give you moles, but I will also give you liters, and you need to take that into consideration. So this is how we set these up. I have my reactants, I have my products. Okay, so along the side, I'm going to set up an ICE table. CE. Okay, and we can do it for reactants and products. So you kind of want to separate everything out. So I is initially how much I started with. So it says I have a 4-liter flask, has 0.20 moles of N2O4. So remember, this has to be concentration. So I'm going to be 0.20 moles over 4 liters. So whatever that is for molarity. If I don't mention the products, that means I didn't start with any. Okay, so 0. So if it's unlisted, it's none. So none if unlisted. Okay, you can assume that. All right. Now the change, remember I said, is stoichiometric. So first of all, these need to have a sign. And what I mean by that is you need to make it negative if it's decreasing in amount, and positive if it's increasing in amount. Okay, in order for this to reach equilibrium, we know that some of products are going to have to be made. In order to get a K value, we're going to have some reactants gone, used up, to make some of the products. So we actually know that the reactants, we're going to lose some, because some of them are going to be made into products. So most of the time, your reactants are negative and your products are positive, not always, and I'll talk about that later. Now, remember I said these are stoichiometric, so we need to take into account their coefficients. So this one changes by amount X, whatever that is, And this one will change by amount 2x because it has a coefficient of 2. So your change rows are always going to look like this. They're going to have x's. They should have a sign, and the coefficient should be brought down as well. And I said equilibrium is just these combined. So 0.20 over 4 is 0.05 minus x, and then 0 plus 2x is just 2x. All right, so all I did here was add I and C. Now, if this was an actual problem, I'd have to give you more information to actually figure something out, but this is how you set up your ICE tables. All right, so we're going to do some example problems. The only way to get good at these is to go through examples. So there are multiple on Chem 101 that I left out the drag and drop ones because they're kind of a pain. And I'm going to go through ones on here, and there's some in, or one or two, not very many, in the group activity for this unit. Okay, so solving ICE problems. Essentially, you need to set up your ICE table, and then you can set up an equation that equals to K. So like K equals products over reactants. So if you set up those two things, you can solve for whatever the problem is solving for. Okay, so example number 8, I'm going to walk through. I gave you a lot of space for this one for a reason. So decomposition of SO3, I gave you the reaction here, is initially charged with 0.012 moles of SO3. So I know that's initially. If at equilibrium, I told you one of the equilibrium concentrations. Now, if I gave you another one, we would have been able to figure this out without having to set up an ICE table, but I only gave you one. So we will have to set up an ICE table. Then what is the value of the equilibrium constant? So the whole goal is to figure out K. All right, so I'm going to set up an ICE table. Usually I will rewrite the equation just kind of spread out so I can have some space. 2 plus O2. Okay, I'm going to do my initial. So initially, let's see, I put in 0.012 moles in 2 liters. So I'm just going to write that here, 0.012 over 2, whatever that is. I didn't start with any products. Okay, so my change, I know I'm going to use up some of these. And instead of being x, this is 2x because the coefficient is 2. That one's going to change by 2x. And I'm going to make some products. So this one's going to be positive 2x. And this one is just going to be positive 1x because it doesn't have a coefficient. Okay, so stoichiometric coefficients brought down. Equilibrium is these just combined. So this is 0.006 minus 2x. This is 2x, and this is x. All right, now the other thing I said is we have to set up a K equation. Now we know for this equilibrium that K is going to be SO2 squared times O2 over SO3 squared, right? So now what I'm going to do is I'm actually going to plug in, or I want to solve for x somehow. All right, now if I gave you K, we could kind of solve for x that way. But in this case, I have one more piece of information. I said at equilibrium, the vessel has this many moles of SO3. So I can actually go down here to SO3. I know that this equals whatever that molarity is, 0.0048 over 2 moles per liter, right? That's a molarity. So I can actually solve for x this way. So I'm going to do that. A 0.006 minus 2x equals, I'm going to put my work over here. So 0.006 minus 2x equals 0.0048 over 2. Oh, I was looking at the wrong problem. Okay, I got that x is 0.0018. Okay, let me erase this down here since I rewrote it over there. Okay, so I know x now, so I can actually solve for all of these concentrations, and then I could plug them back into K. So I already know this one is whatever 0.0048 over 2 is, so that was that was a silly math blip. So this one is oh, come on, let me write. There, 0.0024, right? I already know that one. I know this one is 2x, so 2 times 0.0018. So this one is 0.0036 molar. And this one is just x, so it's 0.0018 molar. Now that I have all these equilibrium concentrations, I can plug them into my K equation and solve for K. So I would do 0.0036 squared times 0.0018 all over 0.0024 squared. Okay, you should end up with K is 0.0061. No units on K. All right, so that's kind of one example of a standard ICE problem. Okay, if you can set up K and you can set up your ICE table, I will have given you some other number that you can use to actually calculate what I'm looking for. Okay, so if you want, I would try examples number 9 and 10 by yourself. I am going to walk through 9 really quick because it talks about dissociation instead of just what the equilibrium amount is. So like I said, I'm going to walk through 9. I'm not going to walk through 10, but I would try these and then check your answers. Okay. So number 9, I'm going to set up this way. I got my ice, C, E. Let's see, I got a 5-liter flask and 0.10 moles of N2O4. So let's see, that's 0.1, right? Nope, sorry, that's not 0.1. I was looking at the wrong problem again. That is 0.1 over 5, right? Yes, so that's 0.015. 2 molar. No. Sorry. Math today. Okay, so initially this is actually 0.02. I was doing the math for the other one, and I didn't put any of this in to begin with. So I know my chain is going to be minus x. This one is going to be plus 2x. So this is 0.02 minus x, and this is 2x. Awesome. So here's the thing. The only other information I gave you is that it's 24% dissociated, and I'm trying to find K. Now, 24% dissociated just means that it will have broken down by 24%. So X, the change is going to be 24%. So what is 24% of what I started with? O2 times 0.24 is 0.0048. So X is this, 24% is X. Okay, so now I have X, I can plug this in, I can find each of these. So this is going to be 0.0152 molar for this guy, and 2X then is 0.0096 molar, and I can plug these into my K equation. And I know K is NO2 squared over N2O4. Plug these in, I got 0.0096 squared over 0.0152, should get 0.0061. Oh my gosh, that's what I did. And the top one, you should not have gotten 0.0061. That one should have been 1.7. I am losing my mind. Okay, so I changed it. Example number 8 should have been 1.7. Example number 9 should be 0.0061. Got a whole lot of math going on. Sorry, guys. So that's what you should get for that. So that's another way to do it. So try number 10 by yourself. Pause it, give it a shot, and come back and look at the work that I have. Okay, so what you might have noticed in this one is the other piece of information I gave you is K value this time, not one of the equilibrium concentrations. So I actually haven't finished this yet. I got my ICE table all set up, make sure your ICE table is right. And I have 49.7 equals, and then what I did is I substituted in these values in my K equation. So it should be HI squared. So I took HI, which is 2x squared, over 0.1 minus x, and I squared it because it's just H2 times I2, and they're the same. So this is the equation that I have set up to solve for x. Okay, so essentially, again, what I did is I plugged in my equilibrium concentrations into my K equation, and now I can solve for x. This one's actually pretty easy because I can just square root it to get rid of these squares. If this was not like this on the bottom, you would have to use the quadratic equation. But this one's actually pretty good because essentially the square root of 49.7 is 2x over 0.1 minus x. And then you can use your solver on your calculator if you want to, or you can do all the algebra by hand. Should get that x is 0.0779. All right, so what are we even trying to find here, right? It says, what is the equilibrium composition? That means like, what are each of the equilibrium concentrations? So I'm going to plug in my x, and then I will get that this is 0.0221 molar. This one is the same, 221 molar. And this one is 0.1558 molar. That's too many sigfigs, but that's okay. So these are each of my concentrations. So these are the answers I'm looking for. Okay, concentration for each one. All right. Now, example number 11 says, suppose that we change the previous problem by increasing the amount of I2 to 1. So the only thing that would change is the I2 value, which means the algebra gets a whole lot more difficult. So it's not that this problem is really much different. It's just that your setup is going to be different. And then you have to do some algebra. So I'm going to set this one up. So try to set that one up if you can, and then check your answer there. Okay, so here's the deal. The only difference in my setup of equation is this 0.2 minus x right here. That's what you get for I2 instead. So in order to solve for this, you have to use the quadratic equation. I am not going to show all the algebra here. You can use the solver on your calculator if you want to, but then I get that x is one of these two values. Now you're going to get two values. Only one of them is going to work, okay? Reason being, you can never have a negative molarity of something. That would mean you have a negative amount, which is completely impossible. So only one of these, when you plug x back into these down here, are actually going to result in numbers that work. And in this case, that is this value, because this one's too big, I end up with negative molarities. So if you do your math right, you should get that your H2 concentration is 0.0066 molar. Your I2 concentration is 0.1066 molar, right? Because I increased it. And my HI concentration is 0.1868 molar. Okay, now you can kind of do a double check on any of these, right? If you get all these concentrations, if I plug them back into my K equation, I should get the K value that I gave you to begin with, right? So if you want to double check yourself, that's a good way to do that. But this does require a decent amount of math. Okay. All right. Number 12 is a perfect one for you to try by yourself, especially after doing all of these examples, because it's just a combination of things that we have been doing. So pause it. Definitely try this one on your own. All right. So what I got here is I got everything set up. Make sure your setup looks good. This one's got two squares again. So that kind of helps out our math a little bit. Should be x squared over 0.40x squared. Those are the same thing, equals 11.8, because that's my K value. I solved for x, plugged them back in, and I got these values. Now, these are subtraction. That's why I only have one sig fig in these answers. Try to keep that in mind as well. All right, so same thing applies for gases, okay? Now, there is one gas law that I kind of want you to keep in mind, and that's Dalton's law of partial pressures. Remember that partial pressures add up to total pressures. That's what his law is. P total equals P1 plus P2 plus P3 plus so on and so forth. Okay, and this is for any gas mixture. Okay, so we're actually going to get some pressures to change when we're reaching equilibrium with gases, and I want you to keep that in mind. So I'm going to do example number 13, and then you guys can try example number 14. So 13 says a flask is charged with 1.500 atmospheres of N2O4 and allowed to achieve equilibrium. Now, I didn't give you the equation, but this is the same equation that we had been using for other examples. I would have given this to you if it was a test problem. So I'm going to start setting up my IS table here. Now, I said you can use molarities or you can use pressures, right? If we're calculating Kp, we should use pressure. So I started with 1.5 atmospheres here, 1.500 atmospheres. I didn't have any of this. So I know I'm going to lose some of this. I'm going to gain some of this. So this is 1.500 minus x, and this one is 2x. All right, it says at equilibrium, the partial pressure of NO2 is 0.512 atmospheres. So I actually know this one, right? Equilibrium NO2. So I know that's 0.512. So that's pretty easy. I can calculate the x is 0.256. Great. Okay, I'm going to put units on this. I got that one. Now I can plug x back in over here, and I can get this pressure, 1.244 atmospheres. And then it says, what's the value of Kp? Easy peasy. Kp is going to be the partial pressure of NO2, right, squared over the partial pressure of N2O4. So I can just plug in my pressures now. NO2, I said, is 0.512 atmospheres. That one needs to be squared. And this one is 1.244 atmospheres. Now it's squared. And you should get that Kp is 0.948. All right. So like I said, try example number 14. This is another good example with pressures and practicing with your IS tables. All right, so in this particular case, I set up my equation and I had K, so I solved for X and then plugged it back in. This would have had to use the quadratic equation or the solver button on your calculator, and you should have gotten that chlorine gas is 3.84 atmospheres And then the chlorine individual atoms gas was 1.31 atmospheres. All right. Now, 14.4 and 14.5 are homogeneous versus heterogeneous equilibrium. We already talked about those in last section. Same thing with calculating an equilibrium constant. We just did how to calculate an equilibrium constant, so I didn't link those. Now, that being said, 14.6 and 14.7, those are parts of the textbook that are unfinished. So what I did is I actually linked a supplemental textbook in the Word document on this. So if you need the textbook to look at more problems, to ask questions, definitely check out those links. Okay, now those are also posted on my website. So we're going to talk about what's called the reaction quotient. Okay, so what happens if I start with both reactants and products in my reaction vessel? Will it go in the forward direction to reach equilibrium? Will it go in the reverse direction to reach equilibrium? That is what we have to figure out. So all of these examples that we've been doing, excuse me, I have just started by giving you reactants. So obviously it's going to proceed forward and make some products. Now, if I give you some of both, which way is it going to go? So how do we figure that out? We calculate what's called the reaction quotient. Now, the reaction quotient is calculated just like K. Calculated like K. Okay. But it doesn't have to be with equilibrium concentrations. But doesn't use equilibrium concentrations. Concentrations. So it's the same thing, okay? It's like products to whatever powers, right? Over your reactants to whatever powers, okay? It's calculated exactly the same. CC to DD over AA to BB, okay? But essentially what it's going to tell you is how far away you are from Q, or sorry, from K, from reaching equilibrium. So how do I use this? Essentially, if you calculate Q and Q is greater than K, that means that the number is too big. And if you look at Q, if this is too big, that means that I have too many products. So if I have too many products, that means it's going to have to go reverse to actually reach back to K. So if Q is greater than the K, that means it's going to go backward because it has too many products, because too many products. So in order to actually reach the K value, I need my products number to decrease and my reactants number to increase. So it's going to go backward. The opposite is true is, of course, if Q is less than K. Now, if Q is less than K, look at how Q is calculated again. That means that I don't have enough products. I have too many reactants. So it's going to have to go forward, okay? Because there's too many reactants, because too many reactants. Okay, now if Q equals K, then that means you're already at equilibrium. But essentially, we're trying to get to that K value. So is it going to go forward? Is it going to go backward? We can determine that based on the Q value. Okay, so we're going to do some examples to determine if it's going to go in the forward direction or the reverse direction. I'm going to calculate Q in order to do that. So it says determine to which direction will proceed. Is it going to go forward or reverse to get to equilibrium for each of these reactions? Okay, and I gave you that the K value is 25. I'm not changing any temperatures, so the K value for this reaction is always 25 and 900 Kelvin. So I'm going to calculate Q. Now I'm going to write my K equation over here just so we remember. It's SO3 squared for the way this one is written times SO2 squared times O2. Okay, products over reactants. So now I'm going to plug stuff in. So Q value for A is going to be SO3. Notice these are concentrations. This is in a 1 liter vessel, so that one's just going to be 0.20 molarity squared over, let's see, SO2 is 0.10. Again, it's in 1 liter, so it's that many molarity squared times 0.050 molarity. Okay, so you should get here that Q is 80. Now, if K is 25, that means that Q is greater than K. So I got too many products. So that means that it's going to go in the reverse direction, or it's going to go left. It's got too many SO3, too much SO3. It's going to shift so that I can make some more SO2 and O2 to balance out to that K value. Okay, so it's going to go in the reverse. All right, you try B and C. Don't forget about the liters there. Do the concentrations, not just the mole. Okay, so if you calculated Q for part B, you should get 1.13. So Q is less than K. So that means that the value is too small. I actually need to make more products. So I need to make more SO3 so I can get to the right number, which is 25. And if you calculate C, you get 25. If Q is equal to K, then I'm already at equilibrium. It's not going to go forward or backward. All right. One way that people have told me they remember is whichever way your greater than or less than sign is pointing is which way it's going to go. But that would require that you always write Q is greater than or less than K. So if Q is greater than K, it's pointing in that direction. It's going to go to the reverse. If Q is less than K, it's going in that direction. So it's going to go forward. So if you want to remember it that way, that's totally fine. But if I ask you to explain why, you should say, well, Q is too big. It has too many products. It has to go in the reverse reaction in order to make more reactants, so it can get to K. Right. So there's actually a very practical application of that, of this, what I'm talking about, and that is Le Chatelier's principle. So this is actually extremely useful for any reversible reaction, and that is to figure out what's going to happen. Is it going to shift forward or shift backward whenever I stress a system? So again, this is not in the textbook, so I provided a supplemental link if you need to go see it. All right, so Le Chatelier's principle is actually very simple. It is for an equilibrium system, okay? If I stress it, so if an equilibrium system is stressed, and I'll talk about what that means in a minute. If it's stressed, it is going to shift. It will shift. It'll either go forward or backward. Okay, so go forward, backward, reaction-wise. It'll shift that way to essentially relieve the stress, or get back to equilibrium. Okay, so re-establish equilibrium. Okay, so if you stress a system, it's going to want to shift in order to counteract kind of that stress. Meaning if I add a bunch of stuff in, it's going to have to shift to counteract that stress. And it acts very much like a balance. That's why I have a picture of a balance here. If I put something in, it's going to have to even back out. So I'm going to show you how to figure out how that happens. So practical use is in the Haber process, and this is how we make ammonia for fertilizer. Extremely important process. It's very favorable in creating ammonia at high pressures and high temperatures. So you can see at the highest temperature and highest pressure here, I'm actually producing more ammonia. So that's for this specific reaction. That's not for every reversible reaction. We're going to talk about why it works this way. Okay. So I want, and this is the Haber process, right? I want N2 nitrogen and hydrogen, and I want to make it to ammonia. And this is a reversible process. And if I balance this, it looks like that. Essentially, I am trying to make this. So I want to shift it forward. I want to make more ammonia, make more ammonia. So what stresses can I do to actually cause it to shift that way? All right. So the three types of stresses are concentration, pressure, and temperature. So I can stress a system by adding or removing reactants or products. Okay, now when you have a system going, it's really easy to add stuff in. But if you're removing something, actually you can get it to like react in a different reaction, or if you have some way to remove it, you can do that. So changing the concentration affects the equilibrium. Changing the pressure, and this is usually done by changing the size of the container. So if I make it into a smaller container, it's going to have a higher pressure. Okay, so changing volume. Or changing the temperature, of course, heating or cooling the reaction. Okay, if you heat it up, is it going to produce more products? Or if you cool it down, is it going to produce more products? And it actually depends on a couple of things. So we're going to look at all three of these. You guys are going to do a lab with these, so kind of keep these in mind. Don't shove them out of your mind just yet. So concentration-wise, and this is probably the most important one, for Le Chatelier's principle. And we're looking at the same reaction here. This is for the Haber process. So the reaction is N2 plus 3H2 makes 2NH3. Okay. And for essentially what happens in this, anytime you add a reactant it is going to shift to the right. So again, I want you to think of it as a balance. If I add a reactant, some of it is going to have to shift and make products in order to reestablish an equilibrium. So if I add something in, it's going to have to shift to the other side in order to balance back out. Now, the same is true as if I remove something. So if I take some out of here, it's going to have to shift backward toward wherever I took that stuff out to actually reestablish an equilibrium. So if I add a reactant, it would shift right. And if I remove a reactant, it's going to shift to the left. So like if I took some N2 out of here, it's going to shift back to the left in order to actually reestablish that equilibrium, or like fill in that gap. You kind of think of it that way as well. All right, so products, if I add in a product, then it's going to have to shift to the other side to balance back out. So if you add a product, it's going to shift to the left side to balance back out. If I add in a bunch of product, it's going to have to shift back to the reactants to even out. And if I remove a product, it's going to shift right to kind of fill in that gap. So if I take out some NH3, it's going to have to shift to fill in that gap. I take some out, it's going to have to shift that way to fill it back in. Okay, so this is actually a graph of me stressing an equilibrium system. What happens? So in this specific example, I added in H2. Added in H2. So it was an equilibrium. I added in H2. So that's like adding in a reactant. You can see there's a spike there because I added it in. And then over time, you can see that after I stressed it, the H2 concentration goes down, the N2 concentration goes down, and the NH3 concentration goes up. So that would mean that I'm making more NH3 and I'm using up that N2 and H2. So what happened when I added in H2? Well, it went forward to produce more NH3 and it used up some of the N2 and H2, right? So if you add something, it's going to shift away. And if you take something out, it is going to shift toward. So that's kind of how the whole principle works, okay? So in the whole rebalancing, if you add something, the equilibrium will shift away, so to the other side from whatever you added. And if you remove something, it will shift toward whatever it is that you removed to kind of fill in that gap. All right, so that's how concentration works. Now we're going to talk about pressure. I want you to remember Boyle's law for a moment, and that says that pressure and volume are inversely proportional, right? If you put something in a smaller container, it's going to increase the pressure. If you give it more space, it's going to decrease the pressure. All right, and that actually affects equilibrium. So essentially, if you increase the pressure or decrease the volume, same thing, the reaction is going to want to shift because it doesn't have much space. It's going to want to try to have as few particles in there as possible. So what's going to happen is the reaction is going to shift to whichever side has less moles of gas, because the less moles you have, the less pressure there's going to be. So to relieve this pressure, when you put it in a small container, it has to shift to the side that has less moles of gas. So it wants to have as few particles as possible. Whereas if you gave it a bunch of space, it's going to want to fill that space. So if I decrease the pressure by increasing the volume or giving it more space, the reaction is going to shift to this side with more moles of gas. Okay, so if it has more space, it's going to shift in whichever way will fill that space. Okay, so to kind of check this, we're going to look at the Haber process and see if that actually matched the principle that we're talking about. So, right, this was the Haber process, and they're all gaseous. Okay, so I want you to look at this. The reactants, the total moles on the reactant side are 4 moles of gas. Okay, 1 N2 and 3 H2s. Whereas the total moles on the product side of gas are 2. So if it wants to go, it wants to shift whichever way depending on the pressure. So I want it to go to the right? I want to produce ammonia. So I want to shift it to the right. So if I want to shift it to the side that has less moles, this one only has 2 moles, I want to put it under a high pressure. So yes, this does match exactly what we said. High pressure in this specific case would shift it to the right because it has less moles of gas. So it's going to make more NH3 and make more NH3. Okay, so you need to look at the moles of gas when we're talking about pressure. Now, finally, temperature can also shift a reaction. Now, we know temperature does change the K value, and that's why it will shift. The K value is going to change with temperature, and it moves either to the left or to the right based on if it's endothermic or exothermic. So, right, an endothermic reaction is reactants. Heat would be on the left side plus heat. You have to put heat in, makes the products. Whereas exothermic would be like reactants, makes products, and it gives off heat. Okay, so the heat is either a reactant or it's a product. Now, you can think about this just like concentration. If I heat it up or increase the temperature, so if I increase the temperature, it's going to shift to the other side. So it's like putting something in. It's like I'm putting a reactant in. It's going to shift to the other side. So if something is endothermic, if I increase the temperature, it's going to shift right. And if I decrease the temperature, it's like taking heat out. Okay, it's going to try to fill in that gap. It's going to shift left. Okay, and same is true for exothermic. You think of heat as a product in this case. So if I increase the temperature of an exothermic reaction, that would be like adding heat in. It's going to shift away from the heat, so it's going to shift left. If I add heat in, it's going to shift to the left side. And if I decrease the temperature or cool it down, okay, that would be like taking heat out. It's going to shift to the right side to kind of fill that in. Okay, so I want to talk about this example really quick. This is the N2O4 example. Is it endothermic or exothermic? So we can tell by looking at shifts if something is endothermic or exothermic. So this shows you, and you might not be able to see it really well, but this is when it's really cold or it's frozen. So when it's cold, it's clear and it's like all N2O4. And when it's hot, it's brown and it's like almost all NO2. Okay, so if I'm looking at this reaction, N2O4 makes 2NO2, I want to figure out which side heat is on. So when I heat this up, which way did it shift? Okay, I heated it up and it turned brown. So that means it shifted to make more NO2. So if I look at the data, heat caused it to go that way. And when I cooled it down, it turned to all N2O4. When I cool it down, it all shifted to the N2O4 side. So that must mean that heat was a reactant because when I added heat, it shifted to the right. And when I removed heat, it shifted to the left. So that must mean that this is an endothermic reaction. Okay, again, something you're going to be doing when you get to your lab. Okay, so the last thing I want to talk about is kind of application of this and catalysts. So you might be thinking, well, what happens when I add a catalyst? Is it going to shift right or is it going to shift left? And actually a catalyst isn't going to shift the reaction. So, right, a catalyst decreases the activation energy. It actually speeds up both reactions because it affects, speeds up the forward and the reverse, specifically because it lowers the activation energy, well, for the forward reaction and the reverse reaction. So if they both speed up, then it doesn't shift. It just goes faster. That's it. Okay, so catalysts are not going to shift a reaction equilibrium. Okay, so looking at this application really quick, I've been talking about ammonia production because ammonia is extremely important. This is kind of how it works. Yes, they do use a catalyst to make it go faster. Remember, we said we have to be at high temperatures and high pressures to make a lot of ammonia. So high temperatures and high pressures, right? Because if I look at the reaction, my N2 plus 3H2 makes 2NH3. We know that high temperatures cause it to produce more ammonia, so it must be endothermic. Okay. High pressures cause it to shift right because there's less moles on the right side. As this reaction happens, they remove the NH3, and as you take more out, that's going to cause it to shift right. So all of these things cause a rightward shift in this reaction to produce more and more and more ammonia. And a catalyst is just going to make it go faster. right? Why is this important? Well, over 100 million tons are produced a year, which actually uses 1 to 2% of the annual world's energy supply, which is a lot if you think about it, okay? It uses an insane amount of energy, but ammonia is extremely important to drive agriculture so we have things to eat. So that's why I talk about the Haber process. It's a really great example for what we're talking about. Okay, so you guys try number 16, try to figure out what will happen to this reaction, which way will it shift? You can just say right or left or draw an arrow when I do each of these things. All right, should get that A shifts to the right side because I added in A, so it shifts away. If I take out B, it's gonna shift toward, it's gonna shift left. If I increase the pressure, it's gonna shift right because there's only 1 mole of gas over on the right, whereas there are 3 on the left. And if I increase the temperature, it's going to shift left because it is an exothermic reaction.